Now that we've talked about Gauss's law in integral form, you can naturally think that what we're going to do next is talk about the differential form version of it. So Gauss's law in differential form. And what I'm going to do is I'm going to start with an intuitive definition. We're going to derive the basic equation, and then we're going to conclude by using the operator that pops out through the course of this discussion, which is called the divergence. So let's start with intuitively what's going on. We're beginning with a review of Gauss's law in integral form. If we start out with, let's say, a positive point charge with electric field lines that go out this way, we have the electric flux density, which is the number of arrows per unit surface area. Gauss's law in integral form says that if we take a closed volume, so any shaped volume here, and if we add up all the arrows that takes place, the total number of arrows, which is also the electric flux density, so the arrow density times the total surface. Again, this circle means that it's a closed integral, so that you're capturing all the arrows that might come out of the volume. That is going to be equal to Q. So if it's a positive number of arrows, that Q indicates that there's an arrow source inside. And if you have a negative value, that means that there's an arrow drain or an arrow sink inside, right? And another way to say this Q is if you have the charge described as a volume charge density, that is going to be equal to the volume charge density integrated across the entire volume, where it's non-zero. So the differential form basically says, let's shrink this so that it's infinitesimally small. So if we have an infinitesimally small closed surface that we're adding up all the arrows into, so there's going to be some arrows going through. You take just a really small section, and what you're going to end up getting is, before over here you end up getting Q. If you take this to an infinitely small volume, you end up getting the charge density rho v. Let's go through the derivation, the transformation from the integral form to the differential form, and arrive at the basic differential form of Gauss's law that you see printed out in t-shirts and all things cool. So starting with the integral form, I'll just rewrite it here. So we have the flux density times the surface area integrated across a closed surface. So again, arrow density times the area gives you total number of arrows, right? Is going to be equal to the volume integral of rho v dv. That's Gauss's law in integral form. Now what we're going to do is we're going to shrink this, and a key feature is that we're going to shrink it so small that rho v is a constant. So rho v could be a function of space, where every location has a different charge density. So to find the total charge, you got to add it all up across everywhere in space. But if we shrink this surface to be so small, we can get to the point where we assume that what's inside is constant. And so if we do that, we can then pull this out and write this as rho v times delta v, where delta v is that infinitesimally small volume. So this is going to be your small volume. So next up, what we're going to do is we're going to divide the delta v over to the other side. So you have arrow density integrated over the surface area divided by delta v is going to be equal to rho v. And here we're going to simplify by just by adding a definition. So when you take the limit of this expression here, so closed surface integral of a vector field, and dividing it by the volume, where you take the volume to go all the way down to 0, that we're going to define as the divergence operator, which we write as del dot d. And that gives us Gauss's law in differential form. So Gauss's law in differential form is the divergence of d is going to be equal to rho v. So in plain English, what that is again saying is that if we sum up the flux, sum up the field lines the flux density across an infinitesimally small region, you end up getting a volume charge density rho v. And in this process, we also introduce this, which is called the divergence. And the divergence we kind of talked about over here is you take a really, really small volume, you count all the arrows coming out of the surface, and then, or you evaluate the surface integral of the arrow density function over the course of that entire surface area, and then you divide it by the volume. And when you shrink that down to 0, you get the operator, the divergence operator. Now the divergence operator is one form of so the divergence is one of the ways that you can do. It's like a derivative for a vector field. So let's talk about this divergence operator a little bit more before we wrap up. So similar to when we were doing vector multiplication, there are different kinds of multiplication. There's like the dot product and the cross product. When you're taking a vector field, so a function that outputs vectors when you input a coordinate, there are a couple ways that you can take a quote-unquote derivative. And so the divergence is the first one that we're going to introduce. And one of the key features is that the input is a vector field. So again, it's not a vector, it's a vector field. So it's a function that where you put in a coordinate, a location, and it spits out a vector. And the output is going to be a scalar field. So the output is going to be something where you put in a location and it's going to spit back a value, right? So charge volume density is a quantity, it's a scalar, it's not a vector, it has no direction, right? So this kind of has similarities to the dot product. Remember that when you take the dot product of two vectors, the input is a vector and the output is a scalar. So this is kind of analogous in that sense. Now, one thing to note is that for the Cartesian coordinate system, the definition kind of relates well to the notation here, but divergence we usually write by saying del dot. And in the case of in the Cartesian system, so this is only valid in the Cartesian, you can define del as a vector d by dx x hat plus d by dy y hat plus d by dz z hat. If you define the del operator to look like this, and you just take the dot product, you end up with the definition of the divergence. It works out quite nicely. Now note that outside of the Cartesian coordinate system, the formula isn't quite so pretty. But for the purposes of when you're in the Cartesian coordinate system, you can refer to the del operator to look like this, and then when you take the dot product, you end up getting the divergence. But let's end this by writing out the definition for divergence in the three different coordinate systems. So if this is in the Cartesian coordinate system, it's going to be, as I mentioned before, d by dx of the x component plus, there's no x hat, remember, because the output is a scalar, not a vector. So d by dx of the x component plus d by dy of the y component plus d by dz of the z component of this vector field. And this x hat means that when you're taking the dot product with d, the x, you get an x dot x is equal to 1, and a y dot y is equal to 1, and a z dot z is equal to 1. So that's why there are no x hats, y hats, and z hats here when you're treating this like a dot product. In the cylindrical coordinate system, it's a little bit different. You have a 1 over rho d by d rho of rho, the rho component of d, plus 1 over rho d by d phi of the phi component of d, plus d by dz of dz. So the z part just works out. And then the spherical coordinate system is even just a tad uglier than that. So for the r component, you have 1 over r squared d by dr of r squared, the r component, plus 1 over r sine theta d by d theta of sine theta times the theta component, plus 1 over r sine theta d by d phi of the phi component. So you can see that between the cylindrical and spherical coordinate system, your formula for divergence is a little bit uglier, but this is basically the formula that you have to plug things into to power through it. And in many cases, as you're solving problems that you might encounter in this class, a lot of these components might end up being 0, so it's a little bit easier to do. But the nice thing about this is that, about the differential form, is that quite often you can't always do an integral easily, but in many cases you can take a derivative. And so when you're this approach kind of allows you to solve for a lot more different problem types. So as a quick review of what we've done so far, we preceded this discussion by introducing the electric flux density, D, and then through that we introduced Gauss's law in integral form, and then by making our volume infinitesimally small, we did a little bit of light algebra to get to the operator, the divergence operator, which gives us the differential form of Gauss's law. And in not so many words, it basically says that if you take the surface integral of the electric flux density function across an infinitesimally small surface area divided by that small volume, what you end up with is, instead of just the charge inside, you end up with the volume charge density. And through this process, we came across the divergence operator, which has a pretty straightforward definition for the Cartesian form, but the way that you would implement this in the other coordinate systems are also given.